In this video, we are going to cover how to calculate genetic probability of a trait that is carried on the sex chromosomes. And so your sex chromosomes, at least in humans, are the 23rd pair of chromosomes, and they are the ones that are different between genetic male and female. An individual that is genetically female is going to have 2 copies of the X chromosome, and so we will write those as XX, whereas the male has 1 X, but then they also have a Y, and that's exactly how we write a male's sex chromosomes. Now, there are different traits that are carried on the X and Y chromosomes, and so when we analyze our traits that are carried on the sex chromosomes, we are going to write each of those traits as a superscript, as you can see here. So for example, let's say that the trait we're talking about, we would use capital A, lowercase a. Not referring to any particular trait. We would write XX for a female, and then whatever her alleles are as superscripts. And so, for example, a male, say if he has a capital A, and then there's nothing carried on the Y for that particular trait, so we wouldn't put anything there. Because males and females have different sex chromosomes, we are going to analyze their sex chromosomes separately. So let's go ahead and do 2 examples. Hemophilia is a blood clotting disorder carried on the X chromosome. The dominant is normal blood clotting called hemostasis. So it is normal that if you were to get a cut or some sort of injury, your blood would clot to form a scab. In an individual with hemophilia, which is recessive, their blood would not clot to form a scab. We're going to cross a carrier female with a hemophiliac male, and then we're going to analyze. So the father has hemophilia, and we know that a male is going to be XY, and if he has hemophilia, we're going to give him a lowercase h. Because he only has 1 allele, he cannot be a carrier, because carrier means a capital and a lowercase. But males with sex-linked traits, they're either one or the other. The mother, on the other hand, because she has 2 X chromosomes, she can be a carrier. So that means one of her X's has a capital H, one has a lowercase h. We're going to go ahead and put their traits on the Punnett Square. I mentioned in my other video that I like to put the male on the top of the box just because I think that it's easier to analyze a sex-linked trait that way. So I'm going to put the father here and the mother on the side. Now what we're going to do is we're going to transfer the traits into the box, but we have to make sure that we take the sex chromosome with it. Just note that when you are writing sex chromosomes, we write X's first, then followed by if there's a Y or not. And then we also are going to make sure that we still put the capital allele before the recessive. So capitals go first, lowercases go second. So let's go ahead and do this as an example. The mother here is going to give an X chromosome with a capital H. The father's going to give an X chromosome with a lowercase h. So we wrote the lowercase second. the mother's going to give an X chromosome with a capital, father's going to give a Y. Mother's going to give an X with a lowercase h, father's going to give an X with a lowercase h, mother gives X, lowercase h, Y. Now we need to analyze. I've definitely seen examples where all of the individuals are analyzed together. I prefer to analyze the females and males separately because sometimes a male is more likely to have a certain sex-linked trait than a female. And so I think that it is worth it to analyze them separately so that you can see how their chances are different based on male versus female. All right. First thing in analysis, we're just going to write what are the options of phenotypes. So dominant, recessive, dominant, recessive. Our dominant is somebody who has hemostasis, meaning that they can blood clot. You could also just write this as normal. Or hemophilia. You could then have normal or hemophilia. And we're going to analyze. We know that normal is a capital H, so of our females, so we're just going to ignore the other side of the box. This is why I like to put the father on the top. Of the females, which is just the left side, only one of them has a capital. So that means out of 2 chances for a daughter, only 1 could be normal. So that makes our ratio 1 out of 2, or 50%. Okay. Now if we go to females with hemophilia, out of the 2 chances for a female, 1 out of the 2 would have hemophilia, which is 50%. So if this couple has a daughter, there's a 50% chance she will have hemophilia. If we do the opposite for the male, now you can see that there's 2 boxes with male offspring. 1 will have normal blood. So that's a 1 out of 2 chance. Or, here we have a lowercase, that's a 1 out of 2 chance of having hemophilia. Okay. Now this just happened to be that it was a 50-50 chance for the females and a 50-50 chance for the males. Doesn't always happen that way. It just did in this instance. So let's do one more example. Colorblindness is a recessive disorder carried on the X chromosome. The dominant trait is color vision, or we can call that normal. Cross a colorblind female with a color vision male and analyze. So the father has color vision, so we're going to give him an X with a capital C, Y. And then the female is colorblind, so she's going to have X lowercase c, X lowercase c. And now we can put them on our Punnett square. Here's the father. Here is the mother. And we're going to transfer them into the boxes. So father gives an X with a capital C. The mother gives an X with a lowercase c. Mother gives an X with a lowercase c. Father gives a Y. Father gives X capital C. Mother gives X lowercase c. And then finally X lowercase c and Y. Again, I'm going to do, normal versus colorblind, because I go dominant, recessive for the phenotypes. So the dominant is normal. The recessive is colorblind. Normal, colorblind. For the ratio, we need to make sure that we only look at one side of the box. So let's start with the females. Females are XX. Both of your females have the normal vision trait, the color vision trait. They both carry the colorblind trait. That means that both of these daughters would have normal vision. So 2 out of 2 females, or 100%, will have normal vision, and none of the daughters would have colorblindness. If we look at the other side of the box, here's our sons. Each of them have the recessive, which is colorblindness. That means that this couple will have 0% of their sons having normal vision, and 2 out of 2 of their sons, 2 out of 2 chance, being colorblind, or 100%. And this is a great example of how the sex of the offspring essentially determines what their phenotype will be. So the female, any daughters of this couple will have normal vision. However, any sons that this couple has will be colorblind. And so the chances are much higher in a male, as the chances for a female are essentially non-existent.